All right, we're going to start this session with some more AI and reinforced learning. Khyathi, could you share your screen?
Yes, of course. Um, could you confirm that my screen is visible?
Okay, we can see your screen, and we can see you, and we can hear you.
Okay,
So you're on.
great. Thank you, Todd. Hi, everyone. I am Khyathi. I am a master's student at UW-Madison studying computer science. And the work I'll be presenting is part of my independent study that I did with Professor Josiah Hanna from the CS department of UW-Madison. And it's been an exciting collaboration with Todd and Greg from the CHTC team. So, very briefly, what I'll be talking about is around dynamic job lease optimization in HTCondor, which is an effort to see if we can reduce compute costs on HTCondor with some AI and ML. Yeah. So before we start, I just wanted to um, like reinforce what is happening under the hood. I'm sure most of you know it, but so when you schedule a job on HTCondor, you schedule it on the access point, which internally runs something known as the Condor Sched daemon, and that spawns an shadow process. And this shadow process would invoke a matchmaking and match your job to an execution point, which is another system which runs the Condor start D daemon and spawns something known as the starter process. And the starter process would basically send periodic heartbeat signals to through the network pipe to say that your job is alive and running on the execution point machine. And when there's like a systemic connection breakage due to, say, like a network disconnection or like a hardware failure, then there would the job would not get terminated immediately. And instead, what HTCondor does right now is goes into a reconnection window, which is like a static 40-minute window where the access point would attempt to reconnect to the job and continue to execute it. So, yeah, with that in mind, the problem that we're looking at is what happens when your job gets terminated all of a sudden. So if you're a CHTC user, you must have experienced this because it is pretty common for it to happen that there's like a network disconnection and yeah, and because of the scale of the problem, there's like thousands of jobs that are being scheduled every day, and there could be many issues due to which the job disconnection might happen. Although we cannot control that, what we can control is how HTCondor would handle it behind the scenes. And our current solution is the 40-minute static timeout that we have. And this is like an attempt to see whether we can do any better than the static value that we have right now. Um, and most of the work right now has been theoretical. We have worked with simulations on an ML model. And yeah, the project is in its nascent stages, and we aim to look at real data very soon. Um, yeah, so the trade-off that we'd be talking about is basically idle time versus job failures, right? So if we wait for too long, then we're basically having slots tied up to the machines that are already dead, and that is just wasted compute. And on the flip side, if we're waiting for too less, then we would be killing jobs that may be successfully connected if we waited for a little longer. So we want to find like a balance of idle time and the jobs that have been failed. Just to understand the scale of this problem, I just have a few slides which show what the real data looks like. We were able to collect some data through the shadow reconnect log that Greg had built. Yeah. So out of the jobs, I think this was on the AP 2001 server that we had in the month of May for like about 2 weeks. And within the 2 weeks window, we saw that there were about these many jobs which experienced a disconnection, and out of the disconnection reconnect attempts, there were around 24,000 jobs that have failed, and 15,000 jobs that have survived the reconnection. And if you look at the disconnect frequency, there are some jobs that recover after a single disconnect, but there are some that even go up to 79 disconnects within that 40-minute window. So yeah, it is a very diverse looking. Uh, yeah, it is pretty diverse in that sense. And this shows how long the job has been running for before the disconnect happens. And you can see that some of the failed jobs have been running even for around 3,500 minutes before they fail. So that is a lot of wasted compute, right? And over here, you can see a 77.3% success rate, which is basically all the jobs that have attempted a reconnection and were successful with the reconnection. This number does look good, but that kind of corresponds to a wasted time of around 3,100 hours, which is pretty significant. So we want to see if we can use like an ML model to optimize on that. And for that, since we did not have a lot of data initially, we wanted to start off with a theoretical simulation of what the system might look like. And for that, we basically used a couple of parameters and optimized on a loss function. So as you can see on the right, as time increases, you can see that the idle cost would increase. So that is the sine increasing graph. And then likewise, if you have more time you spend on reconnecting the job, it is more likely to recover from a failure. So the failure cost comes down, and that would like give us a beautiful curve of the total cost, which shows that we can have like a theoretical optima value that we can set on the system. And we simulated a similar situation using some of these parameters. We scheduled like 5,000 jobs per batch, and used a Pareto distribution, and then simulated some failures using a uniform distribution, and also like 10% jobs were marked as permanent failures. Yeah, and this is a very drastic optimization of what the real system might look like, but I think it's a good starter for understanding what might actually go down in the real system. And we wanted to see if in this sort of a setting, is there any like machine learning technique that we can use to actually optimize and find that true minima, theoretical minima that we have. And when we looked at reinforcement learning basically is to find the best action by trying out various values and interacting with the environment and observing how that value is impacting the environment, and adjusting our strategy based on that. But the main issue with reinforcement learning is that it's extremely data inefficient. Like standard RL algorithms would take around 1,000 steps to come down to a good optimal policy. And the other problem is that we cannot test lots of arbitrary values on a real system where real users are getting impacted, right? So the alternative that we looked at is like a simplified form of reinforcement, if you will, reinforcement learning, which is to basically make use of the fact that we want to optimize on a single parameter, which is the timeout value. And for that, we move towards a Bayesian optimization technique. And yeah, we'll look at what Bayesian optimization is. So Bayesian optimization basically uses the Bayes theorem to combine some of the prior beliefs that we have, the prior beliefs being the model that we fit using the initial data that we have. And as we have new data, the model adjusts to the parameters and tries to find optimal minima in very few steps. So I use this image to like understand on a very high level what might be happening under the hood. That so each with each data point that is being added, our approximation of the model comes closer to what the real distribution may look like. So it uses something called an acquisition function, which it makes a decision rule to balance between exploring a known good data like timeout values in our case, and exploitation is trying to use a more I'm sorry. Exploitation is when you use values that are already known and good, and exploration is when you try to look at a very different value and see if that is adding any value or not. So yeah, it is efficient in the sense that within a very few trials, we can arrive at a decent global optima. Yeah. And so we tried out Bayesian optimization on the simulation that we had. So as you can see in the first graph, the blue curve shows us the distribution of our data. And what in Bayesian optimization, what happens is we initially try out a few random values, which are the blue dots you can see. And once the model has a few random values and sees how the model sees how well it fits to the data, it starts to predict values, which you can see over here are the blue dots. And like our minima for this data was 9.98 seconds. This does not map to the actual data that we have, but yeah, in our theoretical setting, that 9.98 is the optimal timeout value. And on the graph here, you can see how at each step the model tries to identify the optimal value, and as less as 30 trials, the model was able to converge to a value that is pretty close to the optimal value. Over here, this is the Gaussian process surrogate, which is basically like the map of what the AI model thinks is the optimal value. So this band is what the model predicts as the optimal range, and the last graph basically shows the value that has been chosen at each evaluation step. So initially it is random, and then going forward, the model picks out values that are optimal while occasionally exploring new values. And that's what we have so far. What we want to do right now is to transition from the simulation data to actively learning on a real system. We basically want to try out different timeout values and see how well Bayesian optimization performs in the real scenario. And some of the other areas that we wanted to explore is to see if there's any like contextual dependence of timeout value, like an optimal timeout value. For example, if there's a day of the year on which the workload is very heavy, does that mean that jobs crash more often on such days, or is if there's like a systemic failure across all the clusters, then how will that impact the timeout value that we should have, and so on. The other direction that we wanted to look at was to see if we can have like a continual learning framework, if in case the timeout value might dynamically change depending on certain behaviors, and yeah, and then we can identify the timeout value depending on the environment and so on. Yeah, that is all I had for you today. Thank you, and I'll be open to any questions.
Thank you for the wonderful talk, and it really reinforces my preconceived notion that at research universities it is the graduate students that bear the brunt of all the work. So wonderful job. Open the floor for questions. Oh,
While we get the mic around, any thoughts about the challenges of providing you with the data you need in order to make the decisions. You know, yeah, how much progress was made so far, and how do you feel we are in establishing, you know, the streaming of the data you need in order to make, let's call them reasonable decisions.
Right. Yeah. So I think we've been working with Todd and Greg, and they've been able to provide us with some sort of logging information that we're collecting on some of the clusters, and and I was able to like perform some exploratory analysis on those logs, and we were able to see some issues with how the data is being collected. And yeah, I think it's going good so far. Like we are able to collect some data, and then once we have a little analysis on that, we can try out actual values coming out from the system that we would be building. Yeah. So
Okay,
it's
thanks.
yeah. Yeah.
Go ahead, Todd.
I may have just missed something in the slides, but at a few points you make a reference to about 10 being the optimal value. And I thought the point of this was to discover what the optimal value was. So I was wondering where that conclusion came from. Maybe, like I said, maybe I'm just missing something.
Right. Yeah. So basically, this does not correspond to the actual values on the real system. We basically simulated the data using certain parameters, and according to the simulation, the optimal value would be 9.98, like I showed over here. Um, and yeah, and we tried out our model on the simulated data and found that it is able to like discover the optimal minima over here. But we still have to see how it translates to the real world, and yeah.
All right, thank you.
All right, not seeing other questions. Let's give our speaker another round. Thank you.
Thank you.